The last electric field diagram that you should know should be the electric field for a parallel plate capacitor. And in your textbook they show this on page 242. Actually, before we go to this parallel plate capacitor, I want to return to this applet that shows the electric field patterns here. I want to reset this, and just to show you that you can get really complicated electric field maps depending on where the charges are and what kinds they are, then I'm just going to randomly click around here with some negative charges. So there's a negative charge. Now let me go over here and click some positives. You can see that the electric field maps can be very complicated. And the idea is that at each point the electric field is going to be different numerically in strength and different in direction than it will at any other point in space. Yet these electric field maps, if I know what the field is at that point, and if I know how much charge that I've put to feel that electric field at that point in space, then I can figure out what the electric force is. All right, back to the parallel plate capacitor. A parallel plate capacitor is very common in electronics, and we hopefully will have an opportunity to dissect one at some point in class. Perhaps some of you have seen one dissected before, but it consists of a pair of conductors that is separated by a gap. Sometimes the gap is made of air or vacuum. Sometimes there will be some dielectric, some non-conducting material that's put in between the gap. The parallel plate capacitor is going to be something that has a uniform electric field. That's why it's so useful in physics. Let me sketch one. So I've sketched a couple of conducting plates here. One plate has negative charge on it, and the other plate has positive charge. Usually the way this physically is done is to somehow remove electrons from one plate and to deliver them to the other plate. So the plates are charged. And the positive charge plate has just as much positive charge on it as the negative charge plate does. So there's an excess amount of charge on the plates. Here's what the electric field looks like in between. In the middle of the plate, if I'm not close to the edges, the electric field lines are parallel to each other and they are uniform. This would be something like, in the electrical case, what the weight is in the gravitational case. The gravitational field is fairly constant close to the surface of the Earth. Now, if I get close to the edge of the plates, the electric field begins to fringe some, but we're going to, for the most part, use the parallel plate capacitor to create uniform electric fields. When we say uniform electric fields, we mean a field that is constant in magnitude and in direction. So if I were to put a proton in between these plates, the proton would be pushed toward the right. In other words, away from the positive plate and toward the negative plate, because like charges repel and like charges attract. On the other hand, if I were to put an electron in between the plates of this capacitor, the electron would be pushed against the field, away from the negative towards the positive. This electric field that's in between there is uniform if I'm not close to the edges of the plates. I can see that I haven't really left myself enough room to talk about the electric field due to point charge, a special case, but I think that I can discuss that with our first example. Calculate the magnitude and direction of the electric field at point P, which is 15 centimeters to the right of point charge Q, which has a charge of -3 times 10 to the minus 6 coulombs. In other words, -3 microcoulombs. Here's the way I want to approach this problem. I want to approach it by imagining that I put a small positive charge that I'm going to call a test charge, whose charge is little q, at point P. I want to figure out what the force the charge experiences is, and then I want to figure out the direction that that charge is pushed. And from that, then I'm going to take the electric field and say that the electric field is equal to the electric force divided by the charge, little q. Let's do the direction first. That's easy. If I have a positive test charge, little q, and I put it at this point P in the vicinity of this negative charge, big Q, then it's going to be pulled to the left. And since the direction of the electric field is defined to be the direction that a positive test charge would be pushed or pulled, then I can also say that that is going to be the direction of the electric field at that point. So I have addressed the direction part of this question. The direction of the electric field is to the left at point P. If I were in an XYZ coordinate system with X being horizontal and Y being vertical, then this would be in the negative X direction at this point. Now let's go for the magnitude of the force. This obeys a Coulomb's law sort of force. So I can write Coulomb's law for this pair of charges. And now I want to see that the electric field is going to be the force divided by little q. And since I have an expression for the Coulomb law of force, then I can substitute that into my electric field equation. I can see that the little q upstairs in the electric force and the little q downstairs that gets divided out for the electric field are going to cancel each other out. And so I can write the magnitude of the electric field as K big Q over R squared. And so now I can put these numbers in and I'll have myself a result. Now you notice that I have dropped the sign of the charge here. I did not put my negative sign in. I'm going to draw my picture and let my arrow tell me which way the electric field is going to be. So the negative sign in the electric field is like the negative sign in the Coulomb's law of force. It doesn't tell me about absolute direction. It just tells me something about positives and negative charges. In other words, attractive or repulsive forces. So I'm dropping the sign here, and now I put in the numbers and I get something in my calculator. The number I get is 1.2 times 10 to the 6. Now let's think about units. I have a meters squared downstairs. That's going to cancel the meters squared upstairs. I have 1 Coulomb upstairs. That's going to cancel one of the coulombs downstairs, and the units are going to be newtons per coulomb. So to wrap this up, what I would say is that the electric field is equal to 1.2 times 10 to the 6 newtons per coulomb, and it is directed to the left if I'm looking at the point P. That's an example of how to find an electric field if you have a single point charge. Now let's move on to the next example. In this example, I have 2 point charges, QA, which is negative 25 microcoulombs, and QB, which is positive 50 microcoulombs, separated by 10 centimeters as shown. In part A, we're trying to figure out what is the magnitude and the direction of the electric field at point P, located 2.0 centimeters from QA and 8 centimeters from QB. So that's the point that's in between shown in the diagram. And in part B, if a proton at rest is placed at point P, what will its acceleration be initially? And I want to figure out its magnitude and its direction. So let's think about what's going on. First of all, let's recognize that if I'm sitting at point P here, that a little positive charge at point P is going to be pulled to the left by QA, and a little positive charge at point P is going to be pushed to the left by QB. So that if I could get a number for the electric field at A and electric field for B, the net electric field is going to be the sum of those two electric field strengths. Now these are point charges, and I want to draw your attention to the fact that for a point charge, QA and QB, I can write what the electric field is, because if I imagined having some little small point charge, little q at point P, if I divided the force, the Coulomb force, by that little q, I could write what the electric field is, KQ over R squared. So I could write it like this. If test charge little q is placed a distance little r away from point charge big Q, then the electric field due to the big Q at the point where the little q is placed is going to be given by the Coulomb force divided by the test charge. And that will be written this way. The little q's will cancel each other out, and now the final result that I want to get to is that the electric field for the point charge is K big Q over R squared. This is an important formula, but I want to make you notice that this electric field formula is a special case. It's only due to point charge big Q. Well, in this case, I have 2 point charges. I have point charge Q sub A, and I have point charge Q sub B. So I could figure out what the electric field due to point charge QA is, located a distance of 2 centimeters away from the point in question. So at point P, the electric field due to QA is going to be given by this formula. QA is negative 25 microcoulombs. RA is 2 centimeters or 0.02 meters. Again, I'm going to drop the sign here of the charge and let the diagram show me the direction. Let me put in the numbers. And now I can plug them into my calculator and get a result. The electric field at point P due to charge A is equal to 5.625 times 10 to the 8th newtons per coulomb, and that is to the left. I need to do the same thing now for point charge QB and figure out its electric field at point P. And now I put in the numbers and I feed the numbers into my calculator. And I get that the electric field at point P due to charge B is equal to 7 times 10 to the 7th newtons per coulomb, and it is also directed to the left. So now I want to employ the principle of superposition to figure out what the total electric field is. The net electric field at point P is going to be the electric field due to charge A plus the electric field due to charge B, and the direction is going to be to the left. Let's write that down. And now we put in the numbers and put it into our calculator. And I've got a TI 89, so I'm hanging on to all those decimal places that came from the earlier calculations. And my final solution is that the strength of the electric field at point P, due to these 2 point charges, is 6.33 times 10 to the 8th newtons per coulomb, and it acts to the left. That's part A. Now part B says, suppose I put a proton at this point. In other words, let me stick a proton right there. The question is, what will the acceleration, the magnitude and direction of this acceleration be when I let the proton go, immediately after the proton is released? Well, I can use Newton's second law to figure that out. Let me sketch a free body diagram. Now I'm not going to include the gravitational force here. It turns out the gravitational force on the proton is minuscule compared to what the electrostatic force is, and we'll talk about why. It actually has to do with the fact that the electrostatic constant K is much bigger than the gravitational constant G, big G, but here is how I would figure out the acceleration. There's my free body diagram. There's an electric force that acts on the proton that pushes it to the left. So the direction of the acceleration is going to be to the left. Well, what is the electrostatic force? The electrostatic force is going to be equal to Q, the charge on the proton, times E, the electric field strength that we just calculated. So now I can figure out what that force is. And Newton's second law says that that is equal to the mass times the acceleration of the proton. So the mass of the proton times the acceleration. Now I've got a relationship in which I've got the charge, the mass, the electric field, and the acceleration all related. I know 3 of those numbers. I'm going to solve for the acceleration. And now I'm going to substitute the numbers. And now I'll feed all that into my calculator. Again, I'm keeping all the decimals that came from my calculation of the electric field in the earlier part of the problem. I calculate that the acceleration is 6.06 times 10 to the 16th meters per second squared, and that acceleration is to the left.